We've already spent some time talking about chemical reactions. Now we're going to expand our discussion to the thermochemistry, the heat changes associated with chemical reactions. Here's the chemical reaction representing the combustion of methane gas. When 1 mole of methane burns completely in oxygen, 1 mole of carbon dioxide and 2 moles of water are produced. 890 kilojoules of heat are also produced in the reaction. When the enthalpy of reaction is reported with a chemical equation, this is called a thermochemical equation. Remember from our last unit, enthalpy is defined as the heat content of a system at constant pressure. When we measure the heat change during a reaction, but do not measure the work done, we refer to our measured value as delta H, or enthalpy. The heat of reaction given in a thermochemical equation refers to the reaction exactly as it's written. Here's that same thermochemical equation in symbol and particulate form. The thermochemical equation tells us that 890 kilojoules of heat are released when 1 mole of CH4 reacts. It also shows that 890 kilojoules of heat are released when 2 moles of oxygen react. 890 kilojoules are released when 2 moles of water are formed. Delta H is not an energy value alone. It's an energy per unit amount. Its units are kilojoules per mole. It is the heat change proportional to the amount of each substance in the reaction. You can relate the quantity of heat to any substance in the equation. What then would happen when this amount of the two reactants are mixed? If each particle represents a mole, we mixed 2 moles of methane with 6 moles of oxygen. First, recognize that you have a limiting reagent and an excess reagent. There's an excess of oxygen present. The 2 moles of methane determine the extent that this reaction can occur. What amount of products form when 2 moles of methane react? We're performing twice the reaction as shown before. Instead of 1 mole of methane reacting, now 2 moles of methane are reacting. This is just like if you make a batch of brownies, then you do it again with double the amount of ingredients. What happens? You get double the amount of brownies in the end, right? Same here. If we use twice as much of the reactants, we'll get twice as much product too. We'll have 2 moles of carbon dioxide formed and 4 moles of water. We'll also have excess oxygen remaining, 2 moles worth. How much heat will be released? If twice as much reaction occurs, then twice as much heat will be released. So 1,780 kilojoules of heat would be released from this process. Consider this question. Calculate the enthalpy change associated with the formation of 3.8 moles of water. Think of delta H like a conversion factor between moles of a substance in the equation and the heat change for the process. We know from the balanced thermochemical equation that 890 kilojoules of heat is released for every 2 moles of water formed. So we're going to write that as a conversion factor. Starting with our given, as always, 3.8 moles of water. We then write the relationship between moles of water and the heat change as a conversion factor. That's 890 kilojoules for every 2 moles of water in the reaction. Then do the math to get the answer, negative 1,690 kilojoules. How often, though, on a test question or in lab are we given amounts already in moles? That's pretty rare. This is a more typical question. Calculate the enthalpy change when 5.45 grams of ammonia react with excess oxygen. From the thermochemical equation given above, we know a relationship between moles of ammonia and the heat change. For every 4 moles of ammonia that react, 902 kilojoules of heat are released. Before we can use that conversion, though, we'll have to convert from grams of ammonia to moles. Same way as we always do, using the molar mass. 17.034 grams of ammonia equal to 1 mole on top. Now we can write our conversion factor between moles of ammonia and kilojoules of heat. From the thermochemical equation, 4 moles of ammonia react when 902 kilojoules of heat are released. Putting that all into the calculator gives you an answer of negative 72.1 kilojoules. It is most definitely necessary that you either write the negative on this answer or write 72.1 kilojoules released. The question is worded in such a way that the direction of heat change is not specified. You must specify the direction of heat change, either with the correct sign or a specifying word, like released or absorbed. What if the question gives you liters? Liters of gas at STP here, to be specific. Well, first we have to convert from liters to moles. In this case, we can do that with 22.4. Then we write the proper conversion factor between moles of the specified substance and the enthalpy of the reaction. Then calculate your answer. Again, it's necessary here to specify the direction of heat flow. Either write the correct sign or use a word that specifies the direction. The heat change is not always written as a separate fact after the chemical equation. Here the heat change is listed in with the reactants. So is this process endothermic or exothermic? If the heat is being added on the reactant side, if heat is acting like a reactant, then this is an endothermic process. The stoichiometry problem is the same, no matter how they give you the information. You just have to be aware of the different ways it can be presented and the sign notation that is necessary. To calculate the enthalpy change for a question like this, when 52.3 grams of sodium hydrogen carbonate react, we first convert from grams to moles using the molar mass of that compound. Then write our conversion factor from moles, 2 moles of sodium hydrogen carbonate in this case, is positive 129 kilojoules of heat being absorbed at the same time. When we solve, we get an answer of positive 40.1 kilojoules. Look back at that first thermochemical equation that we studied. 1 mole of methane reacts with 2 moles of oxygen to produce 1 mole of carbon dioxide and 2 moles of water. This reaction produces 890 kilojoules of heat. What would be the enthalpy value for the reaction shown below? This is the reverse reaction. If 890 kilojoules are released when methane and oxygen react to form CO2 and water, what is the change in heat when water and CO2 convert to methane and oxygen? The enthalpy change would be the same in magnitude, but opposite in sign. If the top reaction releases 890 kilojoules of heat, the reverse reaction must absorb 890 kilojoules of heat. The top reaction would have a negative delta H value. The bottom reaction, same number, but positive delta H. In these thermochemical equations that we've looked at, you may have noticed a degree symbol with the delta H. When we discuss delta H, and later when we get to delta S and delta G, the degree symbol refers to standard thermochemical conditions. This is not the same as STP for gas calculations. For thermochemical processes, 25 degrees Celsius is standard. Gases are considered ideal, and they are considered to be at 1 atmosphere of pressure. Solids and liquids are considered pure, and solutions are standard at 1 molar. One of the most useful functions of thermochemical equations is that we can combine multiple thermochemical equations to determine the delta H value for other chemical reactions. This process works because enthalpy is a state function. Recall from earlier videos that a state function depends only on the initial and final conditions, not on the process used to get there. The heat of reaction depends only on the energy of the reactants and the energy of the products, not on the energy pathway between them. Whether the reaction takes place in one step or a series of steps, the enthalpy of reaction would be the same. This idea was first developed by Germain Henry Hess and is known as Hess's law. Hess's law calculations will look like this. You will be asked to calculate the heat of reaction for a target reaction. You will be given several simpler reactions with their individual delta H values. You have to manipulate and combine the simpler reactions algebraically to write the more complex reaction. You can then add the resulting delta H values to get the heat of reaction for that original target reaction. It's easier to do than it is to describe. We've already manipulated thermochemical equations, remember? If we flip a reaction around, what happens to its delta H value? Its sign changes. If we change the magnitude of the reaction, double the quantities, for example, what happens to the delta H value then? Delta H changes by the same magnitude. We're going to use those same skills here. The goal is to manipulate the given thermochemical equations in such a way that in the end, the equations used add up algebraically to the chemical reaction in question. For this question, I'm going to start with CuO. I'm going to get it in the right place on the reactant side and the right number of them, 1 mole. I can do that with the first thermochemical equation. The first equation will be used as is. But the second thermochemical equation will have to be flipped. H2O needs to be on the product side. If you flip a thermochemical equation, you change the sign of delta H. So this second equation now is H2 plus 1/2 O2 yields H2O. And delta H is negative 242 kilojoules. I can now add the two equations together to get the original equation in the question. Just as in an algebra equation, if something shows up on both sides, cancel it out. 1/2 O2 is on the product side in the first equation and on the reactant side in the second equation. Cancel it out. When we add everything else together, we get our target reaction. CuO plus H2 yields Cu plus H2O. When my chemical reactions combine together correctly, I can add their delta H values to determine delta H for the target reaction. Positive 155 kilojoules plus negative 242 kilojoules equals negative 87 kilojoules. I always recommend starting with a complex or an unusual substance in the reaction in question. So here, I definitely wouldn't start with H2. That's a really common substance. It might show up in multiple thermochemical equations down below. I'm going to start with carbon graphite. I see that in my first thermochemical equation. It's on the correct side, but I don't have the correct number. To get the correct number, I have to double my thermochemical equation, which means I will also double my delta H value. Think about it. If you write the reaction with twice as much reactants and products, you would get twice as much heat produced at the same time. So it makes sense that whatever I do to my reaction, I do to my delta H value as well. Rewriting this equation down below, then, I'm going to have 2 carbon graphite plus 2 O2 yields 2 CO2, and that delta H value then becomes negative 787 kilojoules. Next, I'm going to focus on C2H2. I see that down in my third thermochemical equation. It's on the wrong side, and I have the wrong number. So I have to flip the equation, which will change the sign of delta H. And I'm going to have to cut all my coefficients in half to get the right number of C2H2s. If I cut my coefficients in half, I'll also cut my delta H value in half. Rewriting that equation then, I'm going to have 2 CO2s plus 1 H2O yields 1 C2H2 and 5 halves O2. I flipped the reaction, so I changed the sign of delta H. It will be positive, and now it will be half as much, so 1,299.4. This remaining thermochemical equation I will use as is. It'll get rid of some unwanted things, and it'll get my H2 in there where I need it. Always make sure everything cancels the way it should. 1 half O2 plus 2 more O2s. That's 2 and a half O2s. That is the same thing as 5 halves O2. So my oxygens cancel out completely, as do the 2 CO2s and the H2O, leaving us with just 2 carbon graphite plus H2 yields C2H2. This is exactly the reaction I wanted, so I add up my delta H values. Negative 285.8, negative 787, and positive 1,299.4 gives us a final answer of positive 226.6 kilojoules. Pause the video and try this one by yourself. I'm going to start with MgO. I see that here in my second thermochemical equation, but it's on the wrong side. So I have to flip this reaction. If I flip the reaction, I change the sign of delta H. So this becomes MgO yields Mg plus 1/2 O2. And the delta H value becomes positive 601.6. Next, I'm going to look at NgCl2. That's in the first thermochemical equation. It's on the correct side, and I have the correct number, so I'll use that equation as is. Finally, I'm going to use this third thermochemical equation, but I'm going to have to flip it. So change the sign of its delta H. This becomes H2 gas plus 1/2 O2 gas yields H2O. Its delta H becomes negative 285.8. In these three equations, Mg cancels out. HCl does not, which is good because we want it in our overall reaction. MgCl2 does not cancel out. H2 does cancel. It's on the product side here. It's on the reactant side down here. Additionally, 1/2 O2 cancels out in these two reactions I've written. That leaves us with MgO plus 2HCl yields MgCl2 plus H2O. It's exactly what we wanted to write, so we add up our delta H's. Negative 456.9, positive 601.6, and negative 285.8 gives me an answer of negative 141.1 kilojoules.